Hi everyone, can you hear me? Am I audible to all of you?
Yes,
And is my screen visible to you? Yes?
yes.
Yes, right? Okay, very good. Okay, good afternoon to all of you. So, I think we are in time, right? Okay, so uh, let's start third lecture of combinatorics. Okay, so in today's lecture, basically we'll see uh, regular uh, objects. Okay, so mainly mathematicians, geometers, they are very much excited about regular shapes or some regularities in objects. Okay, so today we are going to see two things. First, we are going to see what is regular polyhedron. We will define first, and we'll see how many of them are possible. Okay, so this is first topic. And after that, we will see uh, some uh, regular, again, I mean, too much regularity is there in finite projective planes. So it's quite, I mean, it is actually motivated from geometry, but it's not only geometry, it is more. Okay. Okay, so first let's see a regular polyhedron. So like last 2 days class, today also we'll have puzzles and all, okay? And we'll see most of the things maybe you will solve on your own. Okay, so hold on. So first let's see what regular polyhedron is. If you understood, so we are going to discuss two main agenda today. One is regular polyhedron, another is finite projective planes, okay? So first see what is regular polyhedron. So I think all of you might be knowing what regular polyhedron is. So regular polyhedron is basically it's a three-dimensional solid figure, okay, and whose faces are all congruent regular polygons. Okay, so what is the meaning of that? For example, if you consider cube, right? So you see all the faces of the cube are basically nothing but square, right? So they are congruent copy of square, right? So cube is a regular polyhedron according to my this definition, right? So also regular polyhedron are also known as platonic solids. Okay, this is just an alternative name. And if you just consider the any regular polyhedron, so it should be the case that each vertex of a regular polyhedron should have the degree same. Means number of edges adjacent to it must be same for all the vertices in the regular polyhedron. Okay, and if you consider any face, then since as I mentioned already, these are all congruent copies of the same shape. So all the faces also should have same number of edges. Okay, and also same number of vertices incident to it. Okay, these are the properties of regular polyhedron. Now the question which we are going to ask in this class is basically how many regular polyhedrons are possible. Okay, that's the question combinatorialist actually would be interested in to figure it out how many regular polyhedrons are possible. So any guess how many would be possible, or do you know the answer already? Is it this thing did you see in your discrete mathematics course? I know that I didn't cover in discrete maths, but maybe CS guys might have learned this. Just I am curious. Did you see this question before? How
Five.
many regular? Five. Okay, so you know the answer already. So it was taught in your class. Yes.
We learned it at school.
Or you learned this at school. So you know the proof, or you just know that this is just five.
Just as a fact.
This is as a fact you have learned. Okay, so you don't know the proof, right? So we'll see how to prove such thing. Okay, yes, you are right. So who asked that answer the question? I didn't see. Actually, I don't know why I don't see people here in my desktop. I want to see you. Maybe show participant. Right. So now I can see you. Okay, good. Good, very good. So the guess is correct, and yes, it has 5 regular polyhedron, and these are the exhaustive set. This is very surprising, no? So regular polyhedrons are only 5, right? At least, I mean, to me, it is very much surprising. But now the question is, how would you prove such fact, right? That's the most interesting part. And any idea? So I am getting some background knowledge. If you are not talking, please mute your machine. This is just a request. Okay, if you are talking, of course, you should unmute yourself. Okay, so the fact is, as someone mentioned, I didn't see his face. I mean, I couldn't understand who was he. So yes, he is right. So basically, you can see these are the only regular polyhedron possibles. And now the question is, how would you prove such thing, right? Okay, first let us see some facts about these regular polyhedrons. Okay, so you know their names, right? For example, this is cube. Okay, what is this? Do you know this name? What is this?
Pyramid.
Pyramid. Okay.
Tetrahedra.
Right. Tetrahedron is the name. Good. And how about this one? This one is octahedron. Right. So this is dodecahedron, right? And this one is basically icosahedron. Okay. So these are the 5 things: tetrahedron, cubes, octahedron, dodecahedron, and icosahedron. And if you see some characteristics, so if you see the count, there are number of faces, vertices, age, number of edges, and vertex degree. As I said, vertex degree of I mean, it is same for particular polyhedron, right? Each vertex has same degree. Similarly, for phase degree means what I am interested in actually basically how many edges are there in a phase. Okay. So you can see basically these numbers. You can count it from here, right? It's not a big deal. Everybody can count it. Okay. Now, before proving this main fact, means as someone already pointed out, we will be having only these 5 regular polyhedron, no more. Okay. Before proving that, we will prove some small facts. Okay. And combining or maybe linking those facts, you can prove the main theorem. Okay. So before proving that main theorem, let us see some facts. Okay. So do you see that that vertex degree times number of vertices is basically 2 times edges? Do you see this? And same for the phase degree times number of phases. This is also, I mean, all these numbers are same. Do you see this? Yeah, it is evident from this table, right? For example, if you just multiply D with V, means this 3 times 4 is 12, and again this 4 times 3 is 12, right? Similarly for here you can see, there you can see 24, right? So basically now the question is, can you give me some argument? This fact is already known to you, I hope. I mean it's not non-trivial thing to prove. You will be able to prove on your own. I mean, using the whatever knowledge you have, using that only you can prove that. So can you give a proof for this first?
Handshaking lemma.
Handshaking lemma, good, very good. So handshaking lemma, you can prove this left hand side, right? And how to prove this right hand side?
For each face, you are counting a particular edge twice. So
right.
Twice
Right. So that's why you got it, right? So it's very easy to prove. D times P is actually 2 times C, and that is also equals to C times. So you need to prove this side and that side. That's the thing. And it's easy to prove. I am not going to, as you have mentioned, it's actually correct. Okay. Now, this is another fact. If you have a regular polyhedron, it's not necessarily regular, any polyhedron if you have, then you can embed that polyhedron in a sphere. Okay. So what is the meaning of embedding? Embedding means if you see the drawing of a regular polyhedron, so it's nothing but some vertices are there, right, and you have connected them via some edges, right? Right. So if you want to embed this, you can see, I mean, you may think of these edges nothing but wires, right? And vertices are nothing but points, right? And you want to embed that in a sphere, you can actually embed all of these, I mean, each of them in a sphere nicely, right? Means you can, keeping the connectivity constraints means the number of each vertex should have same number of same degree and all. Connectivity means this is, if you visualize this as a graph, you can embed this in a sphere, right? Now the question is, can you embed this in a plane? Can you embed each of these polyhedron into a plane? Is it possible? Mrityunjay, can you tell me whether this is possible to embed each of these polyhedron in a plane?
I don't think so.
You have understood? You don't think so. Any other answer? Mrityunjay said no. Okay, any other answer? So you have understood the question, right? We can embed each of these polyhedron in a sphere, right? Means balls. Now the question is, can you embed this in a plane?
Ma'am, what exactly is meant by embedding?
So embedding means, so you can visualize this each of the polyhedron as something like this. Now, your vertices are there. Vertices are nothing but some points, right? And the edges are nothing but some wires, right? Now you have some connectivity graph is there, right? Now, can you embed this connectivity network in a sphere, surrounding a sphere? That's the question. So that you can always do, right?
So
You can always, right? In a sphere, you can embed, right?
Yes.
Yes. Okay, good. Now the question is, can you embed it into a plane? That is the question. So it means, can you draw this graph in a plane? That is the question, without crossing edges. So you have a graph, right, corresponding to each of this polyhedron. You have a graph, right? So graph is nothing but those vertices are vertices and edges are basically connecting them. That is the edge. So that's a graph you will get. For example, if you consider this tetrahedron, then you will have
Yeah,
a graph.
tetrahedron can be embedded on a plane.
Tetrahedron can be embedded in a plane. Okay.
No,
Do you understand? You made a mistake?
I think I made a mistake.
We cannot, because in a plane the most number of equidistant point can be 3.
Okay, first of all, the drawing which I made is not exactly the tetrahedron is, right? I have, so if you see, all the faces should be triangle, right? So this would look like this. So there also one hidden triangle is there. So this picture looks like this basically. Tetrahedron looks like this, isn't it? You have 3 pyramids, something like this, right? And below one is also triangle. Every face is a triangle for tetrahedron. Okay. So now can you draw tetrahedron in a plane? So this is nothing but a graph. So you can draw it, right?
Yes.
Can't
yes,
you draw?
Yes.
Okay, very good. You can draw. So how about cube?
Yes.
Yes. How about this one? This is octahedron, right? Octahedron. Can you draw it? Okay. No, it doesn't look like. Okay, and these are more scary, right? You have stopped over here saying that this is no. So perhaps you are going to say that these are also no. But surprisingly, the fact is basically you can draw all of them in a plane. Okay, these are all planar graph. Okay, why? So if you want to visualize this, this is something like, as I mentioned already, you can draw them in a sphere. Means if you have a ball, then and around the ball you can draw them. So now basically you just consider any point in the ball. So can you hear me? I mean my network is good, right? So if you will be always able to find one point in the sphere which is not any point of this, right? Means they are not vertex. Now you can actually pierce that and you can actually unfold it and you can just keep that in the plane. So that would be the drawing basically, right? So here is one example. Are you with me? So can you Is it am I audible to all of you again?
Yes, ma'am, you are audible.
Yes, right. Because okay, good. So now you can see these figures. This is D equals to K equals to 3, means this is the tetrahedron figure. So it's easy to draw, right? So from here you can draw this, right? This is that graph. This is for the cube, and this is for the octahedron, okay? And this is for dodecahedron is this one, and this is for icosahedron, okay? So all of them you actually can embed in a plane, so they are basically planar graph. All these graphs are nothing but a planar graph. Okay, now basically we are going to use the some properties of a planar graph. Do you know some properties of a planar graph? Do you know such properties? For example, every connected planar graph, if you consider this thing, V number of vertices plus number of faces minus number of edges, this number is going to be fixed. It's a constant number. It's a 2 for any connected planar graph.
Where are you writing?
Huh? Sorry?
Are you writing this anywhere?
Right. So, so are you see? Can you see this, or this is vanished?
Yes, ma'am, that is visible, I guess. For
That
me.
is.
Ma'am, it's visible.
Is it visible to all of you? So I'm just, yeah. So if you want, I can make smaller, and it is. Let us make this bigger. So is it visible? I hope it is visible. Okay. So this is this all you know, right? Can you give a quick proof for this statement? So
We can use induction.
right. You can use induction and prove it. So can you just quickly give this proof? Can you please quickly? This is just a recap, right? So how do you prove such thing?
Ma'am, suppose it is a tree, then we can prove it easily. The graph is a tree.
Okay. So in a tree, how many edges are there and how many faces? How many faces are there in a tree?
In this case, we'll just consider one.
Right, one face. So if it's in tree, it is obvious. But now you need to do something without. I mean, yeah, if it is not a tree. Okay.
Then we can.
Okay.
Then we can consider there exists a smallest cycle, which is not a part of any other cycle.
Okay.
And then we can remove an edge from it.
Remove an edge means you had a tree, then from there you are removing edges. That's what you are saying?
No, I mean we will look at the graph that is created after removing an edge.
Okay, I see. Then?
So we can apply induction on that new graph.
ठीक है. Okay,
and,
then?
Like for
right.
this new graph will have one lesser face and one lesser edge.
Okay. So yeah, so right, good. So that is one option. So if you are actually say, let's say one, what did you say? One less edge and one less face. But it might be the case that the edge which you, I think which you remove, that might be just a pendant vertex was there, right? So then in that case,
it was a part of a smaller cycle.
Oh, part of a smallest cycle. Okay. Acha. Okay. You are saying that part of a smallest cycle. You are okay. That okay. 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 Good. So what was your induction hypothesis then in this case? You need to have some induction.
We start with the tree. Given any number of edges, we start with the tree, and then we induct on the number of edges.
Then you induct on the number of edges. Okay, the base case is a tree, you are saying. Okay, so do I need to really have base case as a tree? Can I just say that I have just, okay, let's talk about just two. I have one edge, right, and two vertices. That's connected graph. That's the smallest possible connected graph, right? So with that, you can actually go ahead, right? Then you can prove. Means you have that for that base case, you have of course this property is holding. Now you have, let's say, your induction hypothesis hold for any graph of with, let's say, n minus 1 many edges, right? Now I am going to add one more edge to this graph, and I can add anywhere that edge, right? Either I can add in between two vertices, or maybe I can add one extra vertex and add that edge. With that also you can, it's similar actually, but just another flavor. Yeah, that's good. So by using induction, you can prove this easily, right? Everybody is okay with this? I think this is already proved and proved in your discrete mathematics course, and all of you know this fact. Okay, now what can you say about something like this? Let's say if I say, can you prove such statement? For example, let's say again, for any connected graph, of course, connected planar graph. Here we are talking about planar graph. Okay. Yes, what do you say? My screen is not shared. Okay, screen is not visible. So I am also surprised why this is not. Yeah, I can see there also it is not coming. Okay, let me reshare my screen. Okay. Okay, share screen. Stop. Okay. Is it visible now? Can you see right now?
Yes, ma'am.
Yes. Okay. This is visible, right? Okay. So now if you see all these, so, oh, sorry. So if you see all these planar connected graph, right? These are all planar connected graph. So what can you say about their vertex degree of vertices? Is it at least 3? And what can you say about the edge degree? Is it at least 3? Is it at least 3? Can you see? For all the planar graph, whichever we got for the regular polyhedron, right? So it means degree is greater than equals to 3, right? And the C, or okay, here I wrote it as C, right? I will be referring that as C only. The degree of face, I will be referring that as C. Here actually it is a mistake, it should be C. Okay, this should be C in the picture. So, and C, the value of C also should be greater than equals to 3, right? For this particular, the regular polyhedron, the particular graphs which we have considered, for them this is true, right? Okay, now, so can you prove this statement that for such planar graph where degree is greater than equals to 3, then the number of edges is going to be less than equals to 3 times number of vertices minus 6. Can you prove such thing? Can you prove such thing? Let's say I am just considering degree is greater than equals to 3. Can you prove that this is going to be the thing? Can I prove it? Or okay, let's don't talk about degree. Let's okay, maybe use this fact that every face has at least 3 vertices. Sorry, it's at least 3 edges, right? Every face has degree greater than equals to 3. Using this fact, can you prove that a number of edges is going to be less than equals to 3 times v minus 6 for such graphs? Can you prove it?
And we can write 2e greater than equals to 3c.
Okay, so yes, so we already have another property, right? So you can use this property. 2e equals to cf, right? So if you know that c is greater than equals to 3, then what can you say regarding cf and 2 times e? Sorry, not c. So c, I'll be replace this by 3, let's say. So 3f and 2e, what would be the relationship between which one is greater
2
than?
is bigger.
Right. So these should be greater than equals to this, right? 3f should be less than, right? So at least 3, the degree of each phase is at least 3, right? So if you just multiply 3 times f, then basically it might not be cf. So 3f is less than equals to 2e. Now using this fact and this Euler's theorem, Euler's formula, then can you, do you get that E should be less than equals to 3 times V minus 6? Are you getting it? Just rewrite it. Are you getting it? So we have V plus F minus E equals to 3, right? V plus F minus, E, equals to 2. Now you want to replace F. So F is less than equals to 2 by 3E, right? Cardinality of E. So if you are going to replace F by 2 by 3 by this expression, right? So let's say I am writing this 2 by 3 times E minus this. Then can you say which one is bigger among this quantity? Which one is going to be bigger? You have added more here, right? In place of F, whatever you have written, that is actually bigger than that F, right? So it should be greater than equals to this. So from here, basically, you got this. You can rewrite this expression and you will get that you are getting this. Okay, so this is one important thing. Okay. Do you get that this is one important thing? Just remember this. So we have in our hand this formula. Along with this, we have cardinality of E less than equals to 3 times V minus 6. Okay. Okay. What else can you say? So from here, can you say something regarding the regular polyhedron?
Excuse me, ma'am.
Yes.
Ma'am,
Yes.
why for any connected planar graph should D be greater than equal to 3?
Okay, for any connected planar graph, D should be greater than D should be greater than equals to 3. No, it might not, right? For example, it's a planar graph.
You wrote it above, I guess, because a tree is also a connected planar graph, I guess.
See, this is a connected planar graph. You can see the D of this vertex is not 3, right?
Yeah.
It's not true for any connected planar graph, right?
Okay, ma'am.
So what do you say, right? So here what
here
I
you
said.
have written. You've written for any connected planar graph.
Acha, okay. So yeah, so maybe yeah. So that's the wrong statement. Okay, no, so right. So it for any connected planar graph, it is okay. We have actually assumed that C greater than equals to 3, right? This we have assumed. So it's not. It might not be true for any connected planar graph, but the planar graph. Oh, sorry. This statement is not true. Might not be true for any connected planar graph, but we have actually this particular statement is true for the planar graph which you are going to obtain from embedding any regular polyhedron into a plane. Okay, right? Why that is actually, yeah, so you can actually, yeah, so that's true for any regular if you are going to embed any regular polyhedron into a plane, then the corresponding graph should have this C should be greater than equals to 3, right? Why? Because the minimum possible one face should have, I mean, the one face might have the smallest size should be 3, right? Not less than that is possible. You can see, right? That should be, for example, it is if you consider this particular regular polyhedron, then this face is a triangle, right? And it has basically 3. Its degree is 3, right? That's the minimum possibility. So that's why we can assume that any regular polyhedron, if you are going to embed in a plane, then for that corresponding planar graph, the value of C is greater than equals to 3. So we have just assumed that in our consideration. And if you are going to assume that, then basically you can get one expression like this. Okay. Is it okay? Is it okay?
Yes, ma'am. So this expression is also true only for these polyhedrons, right? And not for
Ah,
any connected
no.
planar graph.
Right. It's not true for any connected planar graph, but it is true for any regular polyhedron. If you have any regular polyhedron, if you are going to embed it into plane, then it is true for that. Okay, that specific graph. So if you remember that we are actually, what is our main objective here? Our main objective is to count number of possible regular polyhedron, right? So that is the reason we have embedded one regular polyhedron into a plane, right? And we are actually using some properties of existing properties of planar graph and two specific property of this regular polyhedron, right? Okay, so you have got this. Now another statement let us make another statement. Okay, now consider connected planar graph. Okay, if uh, if it is the case, for example, if it is the case that the faces, I mean the connected planar graph, whatever you have, that is triangle free. Okay, if that is the case, then what can you say about it? So in that case, you know, it's a triangle free, right? Triangle free planar graph. So in that case, what would be the value of C? Can you tell me? Again, consider one embedding of a regular polyhedron, right, in a plane, and consider the graph. It might be possible that it might be possible that the graph doesn't have any triangle at all. For example, in this figure, this graph doesn't have any triangle, right? In this figure also there is no triangle, right? It might be the case if the graph is triangle free, right? If the graph is triangle free, can you prove another statement like this? Can you prove the number of edges is basically less than equals to 2 times number of vertices minus 4? Can you prove such statement? So if it is triangle free, then what is the degree of each face? C should be greater than equals to 4, right? Right. C should be greater than equal to 4. Then using the, similar way, the way we have proved E less than equals to 3V minus 6, you can actually prove that E is actually less than 2 times V minus 4. Okay, these are the only 3 things which I need now to prove that
Excuse me, ma'am.
So, yes. Yeah.
So, ma'am, again, is this true for any triangle-free planar graph?
Right. It is true for any triangle-free planar graph.
A planar graph with 2 vertices and 1 edge connecting them, it won't be true for.
So you are saying 2 vertices and 1 edges like this. So number of
2
edges
vertices
is
and 1 edge. 2 vertices and an edge, not 3 vertices. Just 2 vertices.
2 vertices. Okay, so just you have this thing. So number of edges is 1. Number of vertices is which is actually 2, 4 minus 4. 4 minus 4, what is that value? 0, right? So it's not true for any triangle free graph. So that's why I made the point from the beginning. So you consider the regular polyhedron, right? So for that, right? Is it true for any connected planar graph which has this value C greater than equals to 4?
I think we need to have at least 3 vertices.
Right.
Ma'am, we made the point that each face will have 3 or 4, at least 4 vertices.
At least 4 vertices.
That was the assumption.
Okay, if you have
You said that
at
there
least
are no triangles, but they have
right. Yes, you are perfectly right. Yes. So if you have basically, yes, it would be true for any graph. Let's say you have any planar graph. But the base point should be, it is a connected planar graph, right? And it is triangle free. It should be connected planar graph, and number of vertices should be greater than equals to 4, right? So for this, what is the number of edges? It is basically, let us check this. if we have number of edges basically 4 and number of vertices is also 4, so 2, okay, this is holding, right, for this. We are not, okay, we are not actually considering any specific properties excepting the fact that so okay, accepting the fact, okay, there is, okay, another point. So this C times F, right, this property we are actually assuming, so this property is not true for any arbitrary planar graph. So that's the fallacy actually you are getting. So we are assuming this property, right, C times F equals to 2 times C. So this property is not true for any planar graph, right? So we are assuming this property to prove that, we are actually assuming, if you remember, we just mentioned that 3F is less than equals to 2 times E, right? So this property is not valid for any arbitrary planar graph. So there is the fallacy. That's a good question. Okay, it's
Ma'am,
not true
I
for,
think it is true.
yes?
Ma'am, if we consider the the
Hmm.
outside plane as
Hmm, hmm,
one
hmm.
face, then excluding all the closed faces, we if we consider one open face, then this is always true, I think.
This should be true. Okay, it's a triangle free graph, right? So basically, if every face, okay, every face must have greater than equals to, okay, just right. So basically, is anyway, if you are going to sum of this, then also this is going to be 2e, right? And if you can assume that all the faces are basically triangle free, then yes, Ci is greater than equals to 3 for everybody. And how about the face which is basically outer planar, right? So for that face, how many? So for that face is also 4. Yes. I am here. Yes. So though you can't use this property, you can use this property, right? From there, actually, you can say yes. This property is actually, it's a more strong property. Yes. So any triangle-free connected planar graph, this should hold. Yes. But for our
Ma'am,
purpose, we
like
don't need this.
the one you circled in blue on the left slide, I think that would also be true.
For this graph, you
Yes,
are
ma'am.
saying? This graph, see, this is this is not triangle-free graph, right? You have triangle there. This is one triangle. This is triangle.
No,
This
ma'am.
is
I
triangle.
think what you said, that the above equation E is equal to CF is not true for all planar graphs. I think it is true for all planar graphs.
2e equals to c times a. This is true, you are saying?
Yes, ma'am.
How? Why? This,
Ma'am,
I mean, how you are getting this?
uh,
See,
ma'am,
summation of Ci is going to be 2e. That is, I am buying, right? Summation of Ci is going to be 2e, but we don't, I mean, for any arbitrary planar graph, the value of Ci for every vertex, I mean, every faces
yes,
might
ma'am.
not be same, right?
Yes,
It
ma'am.
might
If
not be
C
same.
is constant, then that should be correct,
Ah,
right?
right. If, yeah, that I am agreeing. Yeah. So if C is constant, then it is, of course, you can say, but C might not be constant for every faces, right?
Yes,
So
ma'am.
that's the right. So that's the beauty of this regular polyhedron, right? So that's the particular beauty. But anyway, you have this expression, summation of Ci equals to T, 2e, and if you say that it's a triangle free, then you can say that's it's a triangle free graph. So all the faces must have Ci greater than equals to 3, and for the outer one also Ci is greater than equals to 3. Then basically you can say this statement. This is a strong statement. Triangle free connected planar. It should be connected, planar graph. This is true, right? This is a more strong theorem or strong lemma. Good. Okay, so now you have all these things. Now connecting these three properties, can you tell me something that the number of possible regular polyhedron is not more than 5? So what we have so far is something like this. You have 3v minus 6, right? This is one more important thing. And the another thing is, if it is triangle free, then we have E is less than equals to what is the statement we got? 2v minus 4, right? 2v minus 4. Okay, so you have these two statements. Using these two statements, can you get something? So I am giving you one hint to prove that the number of regular polyhedron is actually 5, not more than that. Okay. Okay, what can you say regarding the degree, possible degree of vertices? Okay, and what can you say about possible degree of each face? What can you say about this? So if let's say E is less than equal to 3v minus 6, so in this case, can you say that the number of, I mean, the cardinality of the, or the degree of each vertices is less than equals to something? Can you say something?
Less than equal to 6.
Less than equals to 6. Okay. Okay, less than equals to 6. I am saying it is actually less than equals to 5. Can you prove such thing? And how do you prove such thing? D is less than equals to 5. Who said less than equals to 6? Yes, you are actually very much close to it. So I am claiming that D is going to be, if this is the case, so this is for general, right? It is true for our regular, I mean the graph which we have in our hand, those type of graph. This statement is true. Number of edges is less than equals to 3 times number of vertices minus 6, right? So can you say that those type of graphs, for those type of graphs, the degree of vertices is going to be less than equal to 5? It cannot be more than that. Can you say that? How do you prove such thing? Okay, use this.
Ma'am, we can use the dv is 2e and
right. So basically you can, so did you got it? So or should I prove it? This is very straightforward, right? As some of you mentioned. So dv is actually 2e, right? So dv is, so if you just this is basically this is e, and you have this less than equals to 3 times v minus 6. So using this fact, you can actually prove that that degree is less than equals, it should not be more than 5, right? Okay. Okay, so D is less than equals to 6 times, okay, sorry, 6 minus 6, sorry, this should be 12, right? 12 by, am I right? Yes, 12 by V, right? So you can see that D is less than equals to 6 minus this thing, right? So it's actually strictly less than 6. So it can have value at most 5, right? So it's strictly less than 6. This is a positive quantity, right? So D is actually at most, the value of D is at most 5. Okay, now what do you know about the lower bound of D for such kind of graph? That we already mentioned, right? For each vertex, the degree should be at least 3, right? For this type of graphs. If you see the figures also, this is a regular polyhedron in 3 dimension, right? So you just consider any polyhedron. So it should have degree, the vertex degree should be at least 3. So the D, the value of D actually it lies in between 3 and 5, right? It cannot be anywhere else. Okay, so now if D is less than equals to 5, so what can you say about C? What can you say about C? Can C be greater than 5? Is it possible? Can C be greater than 5? Is it possible? Another thing. So, okay, before answering this question, let me ask you another question. So, so do you know dual of a planar graph? Do you know dual of a planar graph?
No, ma'am.
No. No, right? Okay, so what is a dual of a planar graph? So if you see, these are all planar graph, right? So the dual of a planar graph is again one graph, and coincidentally it will be planar graph. So how we can draw one dual of a planar graph? So the planar graph, if you consider the faces, right? So these are the faces. So you put now you construct another graph from this given planar graph, where the faces would be your vertices. Okay, so these are my vertices. Let's say these are my vertices. Okay, right. Corresponding to each face, I would have one vertex. And when I am going to put edges in between, okay, so you can see I will put edges in between like this. Means I will connect those vertices via. So basically, if you see this the vertex corresponds to face, right? So I'll put edges in between two vertices if the corresponding faces are adjacent. Okay. So for example, this and this will be connected like this. This will be connected like this, right? So do you understand? So this graph is again one planar graph. You can draw it. Okay, nicely. Given any planar graph, the dual of the graph is also going to be a planar graph. Okay. So now, so if you understood, I hope you have understood the dual of a planar graph, right? Or maybe let me redraw it using another example. Let's say this is a planar graph. Okay. So I'll use different color. I'll use different color to illustrate the dual of the graph. So I have here basically three faces. So I'll draw something like this, and of course I can draw like this. So this is the green one is basically the dual of the graph. Okay, I missed something. Yeah, so I need to also put edges like this. Okay. I need also put edges like this. Okay. Okay. Am I missing anything? Right. So this is the green one is basically the dual of the given red planar graph. Red graph was planar graph. So this is the dual of it. So how we draw this graph? So you just consider every faces as your vertices in your new graph. Okay. And you will add edge in between two faces. Okay. Means two vertices if they are the faces are adjacent to each other. Okay. For example, this and this faces are basically actually this is a multi this is not simple graph which the graph which I draw. This is a multi graph, but yeah, anyway you can understand. So you can actually this is a multi graph which I draw, right? But you can simplify this if you want. You can erase these faces also. Sorry, these edges also. But anyway, if you draw, let's say, draw the graph in bigger way so that you can have a better look at this. For example, let's say this is my graph, okay, and the dual graph would be something like this. So this I consider for the outer face. So this, right, and this face and this face you can draw via this, and this you can draw via this, right? Something like this. So the green one is basically one dual of the given planar graph. So, so can you? Huh?
There
Sorry?
are two edges.
There are two edges. Okay, which are the two edges?
For the face, two faces above.
Two faces above. What is your question?
I
What
think
is your
there are
question?
two more edges in the green graph, the dual graph.
Achha, two more edges. You want to say that you want to connect this via, okay, this edges and that you want to connect. So I have already connected. I don't want to make it multi-graph. If you want, that is also possible. I am drawing it like this. That is also possible. One can draw it. So then this will be multi-graph. You understand? So because I have already put one edge, right, in between this and that. So if you want to draw that also, you can draw.
Oh,
It's not
okay.
a problem, right?
Okay, okay.
So this should be multi-graph in that case. But anyway, so now the question is, yes, okay. Let us draw this multi-graph in that case. That would be then calculation would be much more straightforward. Okay. So this is a multi-graph, not simply graph like this. It might be multi-graph as you mentioned, right? So now, can you tell me? So what is the number of vertices in this?
So, ma'am, why did we add those edges? Like,
Acha, this
why
is
did we
actually,
add those
yes.
edges? Like,
Right, that's a good question. So I want to answer your question, but first answer my question. What would be the number of vertices in this new graph?
Number of faces.
Can you tell me?
the
Right,
number of faces in the.
right, number of vertices in the dual graph is actually number of faces in the original graph, right? Okay, now can you answer my question? So what would be the number of faces in the dual graph? What would be the number of faces in the dual graph? Is there any connection?
Are we talking about the multi-graph or just without the multiple edges?
Right, yes. So in the multi-graph, let's talk about multi-graph. Multi-graph, what would be the value?
Vertices in the original graph.
Right. So yes, so that's why it's okay. So considering multi-graph is okay to have this kind of relationship. Okay. So if you are allowed to draw this multi-graph in a dual fashion. So so now the question is, how many number of edges are there in the dual graph? How many number of edges are there in the dual graph? Can you tell me quickly? Number of edges. The way we have drawn is basically, you can see, I mean, so since this is a multi-graph, right? So we have drawn with respect to every edges this line, right? You can see with respect to every edge we have drawn one line, right? So number of edges in the original graph and the dual graph would be same if you consider this multi-graph. Okay, do you understand?
Ma'am, I couldn't understand why did we draw two same edges, like two edges from
Right.
same pair of vertices?
Okay, that's a good question. As I mentioned, so first of all, even if you draw these multiple edges, right, the graph remains one planar graph. That you can see, right, the way we have drawn it. All right. So now the question is, I mean, now you want to have the beautiful relationship. For example, number of vertices in the dual graph you want to make, so that anyway will be the number of faces in the original graph. And how many number of faces you have, right? And how many number of edges you have in the dual graph. So that number you want to match with the original graph for some purpose, for some calculation purpose, it is very much useful. Okay, so that's why we actually consider the multi-graph. Even if it is a multi-graph, we will draw it. Okay, so to have this beautiful relationship. Does it make
So
sense?
why aren't we adding
Draw
more
these
edges?
multiple edges and when not?
You said that once again.
How do we know when to draw these multiple edges and when not?
Acha, so that's a good question. So, so you don't need to know when to draw the multi edges. So how you are going to draw it. So you consider every faces. There you put just one vertex, right? Now, if you share boundary, you just draw one edge in between. Okay. If you share the boundary, you just draw. So in this, you don't need to remember that whether it is going to be one multi-edge or something, right? You don't need to remember. You just blindly, this is a, what should I say? It's a computationally you can do this easily, right? Without thinking too much. Okay. Okay, very good. Now, why did I ask this question? So, so I hope you have understood this is actually, I hope at least mathematics guys, I mean the maths and computing guys, they already know this dual of a planar graph is going to be a planar graph. I hope you have remembered. So now the question is, if you know the degree of vertices is going to be less than equals to 5, then what can you say the value of C, regarding the value of C? Okay, what can you say regarding the value of C? Can you say something?
3, 4 or 5. 3,
3,
4
4
or
or
5.
so 3, 4 or 5. Okay, so it cannot be more than 5. That's what you want to say, right?
Yes, ma'am.
Yes, right? So if it is more than 5, then what will be the thing? If it is more than 5, let's say.
That whole become
Euler equation won't be satisfied.
Right. That equation will not be satisfied. Good. So you can see the value of C is also less than equals to 5. D is also less than equals to 5. So there are these possibilities 3, 4, 5, both for both D and C. These are the possibilities. Okay. Now let us consider. So as I mentioned already, so you want to have this D and C, right? And we already pointed out the value of the D and C both are actually in this range, both inclusive, right? Now, let's say C is not equals to 3. Okay, then what can you say about the value of D? C is not equals, let's say, if C is not equals to, I am saying, and this is a specific case, so I am just asking you the question. If I know that the value of C is not equals to 3, then what can you say about the value of D? If you know the value of C is not equals to 3, then what can you say about the value of D? Can you say something regarding the value of D? Using your earlier formulas, whatever you have in your hand. So if C is not equals to 3, right? So you know that C is going to be greater than equals to 4, right? Right, for this particular types of graph, right? You know C is anyway greater than equals to in between 3 to 5, right? Not less than that. So if C is not equals to 3, then C is going to be greater than equals to 4. And in that case, the graph is triangle free, right? And we know this property is holding, right? That we have already proved it. So from here, what can you say about the degree of vertices? What can you say?
Will be 3.
D is be 3, right? That's the beautiful thing, right? Yeah, can you prove it? It's very easy. Everybody can check it. So if C is not equals to 3, then basically using this formula, one can prove using this and of course this one, dV equals to 2. You need to utilize this. Using this two, you can actually get that the value of D would be equals to 3. Okay. Okay, now
Excuse me, ma'am.
Yes.
Ma'am,
Yes,
are we
yes.
talking only about triangle-free graphs? Like, you did not mention it yet that we are talking about triangle-free graphs.
No, I am not talking about that. I mean, the proof is not completed yet. So that's just one part of it. So what I mentioned, if the value of C is not equals to 3, then the value of D is going to be equals to 3. This is just one statement. So now you have, right? So, okay. So if the value of C is not equals to 3, the D is going to be equals to 3. Now you have enough clue to prove that we have only 5 regular polyhedron. Can you prove it? We have almost proved everything, right? So now I am asking you the question. So we have enough. So just observe this thing. Then from here, can you conclude that we have only 5 regular polyhedron, not more? From here, can you conclude? Isn't it very straightforward? So what we have proved so far? We have proved that the value of D and C are in this range, right? 3 to 5, 3 to 5. And if C is not equals to 3, then D should be equals to 3, right? That also we have proved. So using this, now it is easy now. So what is the thing basically? So the combination of C and D, what are the combination? So if C equals to 3, then I could have D equals to 4, 4, 5, as well as 3 is also possible, right? This is one possibility. And if it is not 3, then it is 4, then here it should be 3, right? if it is not, C is not equals to 3 means it can be 4, 5. So then D should be equals to 3. So these are the only possibilities, right? Any other thing is not possible. So C and D, the combination of C and D is basically this. These are the condition. So how many things you have? 3 plus 2, 5. So that's the thing. You have only 5 possible values of C and D, and if you check our this regular polyhedron, then these are the possibilities, and that matches with whatever the result we have obtained here, right? 3, 3. This is one option. 3, 4 is another option, right? 4, 3, one option. 3, 5, 5, 3, right? Does it make sense? So this is very straightforward, but I mean it looks tricky at the beginning. How would you prove such statement? Though statement is easy. When how many regular polyhedron you have, that is basically 5. So how you are going to prove such thing? So if you are going to prove such thing, what the main idea is basically, what is the main idea we have used to prove such thing? We have mainly restricted the possible values of C and D, right? So first we prove the value of C and D, they are going to be greater than equals to 3, right? Both C and D are going to be greater than equals to 3, right? Okay, next what we show that if the value of C and C, they are going to be greater than equals to 3, then you have this formula, right? From Euler's equation, you got this. And from there again, from here again, you can show that the value of D is less than equals to 5, right? Now using the dual of a planar graph, right? So you can also say that the value of C is also going to be less than equals to 5, not more than that. Otherwise, otherwise you are actually not maintaining the dual planar relationship, right? So C should be less than equals to 5 in that case. So in other way, so we first restricted the value of both C and D, that is basically in this range, in between 3 and 5. And we also, this is another beautiful thing, if C is not equals to 3, then one can always show that the value of D is going to be 3. It cannot be other thing, right? And that you can basically prove from this statement using this thing. If it is a triangle free, right, then you have this statement, and from here if you just plug in this relationship, then you will get that the value of D is equals to 3, right? Okay, now basically combination. What kind of combination you are achieving, right? Using that you can prove that you have exactly 5 regular polyhedron, and these are the exhaustive set. You cannot get anything other than this, right? Any other combination is not possible. Okay. Any other question? Do you have any question
Yes,
regarding this?
Like
Yes.
if we have a 3D solid whose faces are all polygons, then it can be made into a planar graph.
Yes, it can be made into a planar graph, right?
How?
So if you have a, if I understood it, your question is you have a 3D polyhedron, right? That's what
Yes,
you,
ma'am.
right. So what you can do basically, first you embed the polyhedron in the sphere. That you can always do, right? Means you have a ball, right? You want to draw that graph over the ball. That is always possible. You can draw it, right? So once that drawing is done, so what I am saying, you have a ball, right? So of course you will always be able to find some free space in that ball, some free space. So what you can, you just what you are going to do, you just make a hole in that place, and you just unfold your this ball, right? You tear the ball rather there. So if you do that, then basically you are getting one planar drawing of that thing, right? That whole whatever you had. In this way you can visualize. Otherwise, what you can do basically, you can project your this sphere into the plane, right? Project the drawing whatever you had made over the sphere. By basically, what should I say? You have a hole over here. You just you try to tear the sphere, right? and part it apart, and so that you can actually embed whatever the embedding you are getting over the plane. That is your drawing. So in this way you can visualize, and you can state for, so it's not only for regular polyhedron. If you have any arbitrary polyhedron, convex polyhedron, so you can always basically corresponding graph, whatever you have, the connectivity graph, you can always draw it in the plane. That would be a planar graph. It is true for any regular, any polyhedron, not necessarily regular.
Yes, ma'am. Thank you.
Okay, good. Any other question? Do you have? So this is very simple thing, right? Maybe you are, as some of you mentioned, you know this fact even in high school level. Okay, having said so, now if you don't have any question on this topic, let's move to the next topic, which is finite projective plane. Okay, here again, as I mentioned in the beginning, so you will see regularities. Okay, so in finite projective planes. So basically, mathematicians are always interested in some regular shapes or some regular size, something like that. Whether that thing you can construct or not, that type of question basically combinatory, those who do combinatorics, they will do or ask, right? Okay, before I'll not say more word. First, let us see one simple definition regarding finite projective planes. Okay, first we'll see the definition, then we'll illustrate with example and how, from where these finite projective planes come, how you can relate with real geometry and all. Okay, so what is this? So finite projective plane is basically it's let X be a finite set. Okay, so that's why the finite term is come. It came from, because this is finite. We are talking about finite set. X be a finite set, and let L be a family of subsets of X. Okay, family of subsets of X, or system of subsets of X. Okay. Now this XL, this is a pair. It's called finite projective plane if it satisfies some axioms. Okay, what are those axioms? Okay, before going into the detail of axiom, let me talk about this set and subset, whatever we have, in terms of points and line. Then maybe you will understand these axioms more fast. So you may consider X to be a set of point, okay, and L, whatever you have, those are basically a set of lines, okay. And of course, as you understood, so lines means, so lines will contain some of those given points. Okay, so if some line has, so for example, you may consider, let us say, yeah, these are my 3 points. So right, so this is my X, and maybe these are, so this is one L, this is another L, right? And let's say I have these are the only 2 L that we have. So this is L1, this is L2. These are the only things which consist of this L, curly L. So now the question is, what type of axiom we should satisfy to say that XL is one finite projective plane? Okay. So the first property is something like this. There exists 4 element set F, which is of course a subset of the given X, means 4 point. In other words, there should exist 4 point such that, okay, I did a mistake here. L, it should be L intersection F should be less than equals to 2. The cardinality of L intersection F should be less than equals to 2 for any L, any line you pick from the given family of subset. Okay. So in other words, so what is the meaning of this axiom? This 4 element set, whatever you have, that F, that so it should be the case that there should be, able to find no 3 of which are basically collinear, right? If you have a set of point F, right, let us say I have 4 points such that no 3 of those points are collinear, then basically this property will automatically hold, right? Am I right? right? So this is that axiom. First axiom, it says that there exist a 4-element set F, which is a subset of the given X elements of set, and you take intersection with that F with any of your line, then that cardinality should be less than equals to 2. It should be true for any L. Okay, this is the first axiom. And the second axiom, so what is the second axiom? It says you take any two distinct line from your given family, okay, then they should intersect in exactly one element. In other words, if you consider the intersection of L1 and L2, it should contain exactly one element, not more, not less. Okay. Okay. What is the third axiom? The third axiom is basically it says you consider any two distinct element from your given set X. Okay. So it should be the case that there exists exactly one set L in L that contains both x1 and x2. Okay. In other words, if you consider any two distinct point, then there should, I mean, in your family of lines, there should exactly be one line passing through both these points. Okay. So these are the three properties which should be satisfied to make one set system to be a finite projective plane, right? Do you understand these properties? So what I said in the first property says there should be 4 points, no 3 of which are basically collinear, right? Right. You can visualize this in terms of points and line, but it may not be. I mean, not necessarily they should be points and line. It can be arbitrarily set system. Okay. So that's why, I mean, though the motivation came from geometry, but not necessarily this the set X and the L, they should be point and line. It may not be. Okay. Just you should satisfy all these properties. These 3 properties should be actually satisfied. Then only I will tell that, okay, this is a finite projective plane. Okay. Okay, so I hope you have understood it. Now the question is, can you give one example of a finite projective plane? For example, if I have, let's say, 3 points like this, and I draw these 2 lines like this, right? So then basically I have, let's say, so X is basically this 1, 2, and 3, right? So you have the definition of X, 1, 2, and 3. And L1 and L2 is like that, whatever the way I have defined. Now the question is, does X and this L, the way we have defined here, is it a finite projective plane? Does it satisfy these properties? Does it satisfy the properties? Is it a finite projective plane? The example which I gave.
First property is not satisfied.
It is not satisfying, right? All the properties. Which properties are violated?
P0.
Post one at least.
Right. P0 is not satisfied, right? Good. And how about P2? Is P2 satisfied?
No, ma'am.
Yeah.
No, right? So point 1 and 3, you don't have any line, right, with respect to them?
Yeah.
So P2 is not satisfied. How about P1? P1 is satisfied. Any two distinct line, you have exactly one, so they have exactly one. P1 is satisfied, but P2 is not satisfied, and P0 is not satisfied. So now the question is, okay, so can you give me a finite projective plane of smallest, I mean, with smallest size or something like this? What would be your finite projective plane? Can you construct some example of finite projective plane? Is it always possible to have a finite projective planes with any number of points? Say X, let's say X I have n many points in it. So is it possible to have a finite projective plane with any arbitrary value of X, I mean cardinality of X? Is it possible? Okay, that is the question. Now that is actually, I mean, more combinatorial question. But before having the answer and all, I would like to give you some example of finite projective plane, and I will also illustrate. I'll illustrate you with one puzzle. Okay, because puzzles are always very interesting, right? Though I don't have much time, but I'll try to cover up. Okay, this is one example of a finite projective plane. Okay, this is known as Fano plane. Okay, you can see. So these are the point. These dots are basically points, and the lines are basically the curves or the line segment, whatever I have drawn. Those are the basically line. You can see, for example, the line A is actually containing 1, 2, 3. The line B, it contains the point 3, 4, 5. And can you check it quickly whether it satisfies all the properties of a finite projective plane? That it satisfies? I already mentioned, Joe, that this is a this is the thing. Okay, let me try. Okay, how to make it right now? You can check it. Can you quickly check that it is whether all the properties are satisfied? So P0 satisfied? So is there any? So do you have F here? What is the F? So what is the property of F? F should have 4. I mean, F is a set of 4 points, right? So that no 3 of them are collinear, right? So do you have such thing here?
Yes, ma'am. We can take the 3 vertices and the center point.
Okay, right. So 3 vertices and the center point, right? No, there is right. There is no line which passes through all 3 of them. Sorry, all 4 of them, right? Okay. No, okay, right. No 3 of them, right? So P0, you got it. So how about P1? You can check that for any 2 distinct line, whatever you have, they are actually meeting in exactly in 1 point. You consider any 2 line. The circular one is also 1 line. Okay, so which is actually passing through 2, 6, and 4. That is also considered as a line according to our definition. Okay, 2, 6, and 4. 1 line passing through 2, 6, and 4 only. So okay, so that line, so so that name of the line is actually, we are referring that as G. So G, if you see, it intersect with B in exactly 1 point. That point is 4, right? G and B, this line and this line intersects exactly in B. And you can check that for any pair of line, you have basically 1 intersection. For any pair of line, there is exactly 1 intersection point. You can check quickly. Okay. And for any 2 distinct element also, there is exactly 1 line. If you consider any 2 pair of point, for example, 6 and 2, okay, they are passing through 1 line, right? So that line is G, right? So you can check it. So this is one smallest example. Okay, but okay. Question is, why should we study such thing? That is the main question which I should ask, or maybe one of you should ask. Why should we study? Without motivation, I will not study anyway. Okay, now let us come back to one puzzle. Okay, so it says something like this. Let's say we have 7 policemen. They are transferred to a new place. Okay, and they came from different places. Nobody knows each other. They are completely new. And 7 of them are there, by the way. And we need to make a schedule or shift of 3 men. In a schedule, I mean, in a shift, there should be 3 policemen. Okay, during, I mean, and we need to make a schedule for a week. Okay, and of course, we should make a schedule in such a way that because they want to know each other, right? So they have come, and I mean they are new to the place, so, and they don't know each other. So it should be that the schedule should be in such a way that every 2 policemen should be able to know each other in their schedule. In any of the, I mean, in any of the shift, it should be the case that 2 policemen, I mean, each pair of policemen should be in any of the schedule, right? In any of the schedule. You should ensure that. So not only that, we also should ensure something like this. It should not be the case that same number of, it should be the case that everybody is actually in the same number of shift. It should not be that for one policeman, it is actually he has all the all the days he has a duty, right? It should not be the case. Okay, right? This is also one important thing. Another important thing is no policeman should give consecutive 3 days of duties. Okay, more than 2 days is not allowed. They are allowed to come consecutive at most for two days, not more than that. This is also important. Okay. But since maybe they don't only actually meet for knowing each other, but also since this is a important place, right, and maybe some criminal work or something is going on, they want to solve some puzzle also, right, a real puzzle. So it should be the case that the story, whatever they have started from the first day, it should be continued from up to the last day. In other words, let's say in a first day schedule, we had some 3 policemen, arbitrary 3 policemen. It should be the case that in the next day's schedule, 1 policeman should be there from the previous day's schedule. Okay, because they want to know what happened yesterday. Okay, so these are the constraints which you have, right? So using this constraint, can you construct a schedule for the policeman? Okay, that is the question. So can you answer this question? So this is one puzzle, okay, famous puzzle, policeman puzzle or scheduling puzzle. Sometimes it is also known as secretary problem, secretary puzzle. But that puzzle statement is different than this. So this is basically scheduling shift of policemen. Okay, yeah, we have 7 policemen, and we want to schedule them for 7 days, okay, in a week. In such a way, all these properties are satisfied. Now, can you give me some schedule? So let's say I have 7 policemen, right? I can number them 1, 2, 3 up to 7, let's say. Can you give me a schedule of this, guys, so that you have all the properties satisfied? Can you give me the answer? Okay, first let us forget about this last statement. Everyone has the same number of shifts, that is okay, and forget about other constant. Okay, let's forget about this other constant. I am not talking about. Let's say I am interested to have one schedule such that everyone has the same number of shifts. Okay, this is important, and every 2, right, this is also important. Let's say every 2 of the 7 men have a common shift. Okay, that is also important, and forget about the other constant for the time being. Let's say let's say I have just these 2 constants. Every 2 of the 7 policemen, they should have a common shift, that is one constant, and the other constant which I am just making is basically everyone has the same number of shift. Okay, with these 2 constraints, can you make a schedule? Only these 2 constraints, can you make a schedule? Can you make a schedule? First of all, let me ask you the question. So did you understand the puzzle? If I just forget about the other parts, let's concentrate on the marked part, means the blue marked part. Okay. So can you tell me whether you can have a schedule for the policemen so that every 2 of the 7 men have a common shift and everyone has the same number of shifts? Can you solve it? Okay, should I give one hint to you? Okay, I think it is actually, it's not so obvious puzzle. I mean, obvious to answer. Okay, right. So I should give a hint. The hint is basically the phenoplane. Okay. Now I have given you the hint. So can you quickly see what should be the schedule? So as I said, 1, 2, 3 up to 7, these are my policemen, right? So let's consider these as your schedule, 1, 2, 3 in one day, 3, 4, 5 in another day, 5, 6, 1 in another day, right? Then maybe 1, 7, 4 in another day, right? Then another next day will be 4, 2, 6, right? Then 6, 7, 3, right? Now in the next last day you may be 2, 7, 5, something like that you can do. But now, so if you just make that, so you can check everyone has same number of shifts, right? So for example, 1 would be exactly in 3 days. 3 would be exactly in 3 days, right? 4 would also be the policeman number 4 would be in 4 days duties, right? So this property is satisfied. 7 men have every 7, I mean, all of them has a same number of shifts, that is satisfied, right? Okay, so just a minute. I should draw these as well. Okay, very good. Right. So, right. Okay. So now, can you quickly check that all the 7 men have common? I mean, every 2 of the 7 men have a common shift here. What is the meaning of that? Every 2 of the 7 men means every pair has a line, right? Every pair should have a line going through it, and that is the property of the finite projective plane, right? Every 2 of the 7 men. So you can consider the policemen as points, right? And the shift as line, right? So in other sense, each line should contain 3 exactly. I mean, 3 here is basically it contains exactly 3 men, right? Okay, and all the policemen has same number of shifts, and that's the basically the degree of this graph, right? So here basically, for example, the policeman 5 has 3 shifts, right? Okay, now the question is, if I want to add the other constants, for example, no one has more than 2 consecutive days, right? We need to arrange the schedule, right? Right? Then how do you do such thing? Can you do it? Right now I want to add this constant. Why I am not listening any voice? No one has more than 2 consecutive shifts, right? More than, and basically every shift has 1 man who was also present in the previous day's schedule. So how will you do that? How will you do that? Is the question, I mean, did you understand the question? The puzzle, did you understand? Hi everybody, I mean, I am not listening your voice. Subhan?
Man, for the
Yeah.
third part, is it just equivalent to walking over those lines without lifting up a pen?
Right. That's the guess. Good. Yes. That is the answer basically. Yes. If you want to draw this graph, right, without lifting pen, then basically you will get the answer. If you want to satisfy that every shift has a man who was also present in the previous day's schedule, then basically that is the way basically, right? If you want to draw this graph without lifting pen, then basically you will get that answer. That schedule you will get automatically.
I think that is quite famous. So I guess since there are more than 2 vertices with odd degree, so we cannot do this. Like 1, 3, 5 both have degree 3. So
okay,
we won't get. We cannot satisfy.
1, 3, 5. So okay, all of them has degree 3. So you cannot do this, right? So in other word, you want to say that every shift has 1 man who was also present the previous day and knows what was going on, etc. Okay.
No, it's not drawing the graph without lifting the pen, right? For example, if one shift was 174, the next shift could have been 572, which was
174. Okay, 174. Next shift could be, what is your next shift?
572.
174 572. Yes.
Yeah,
Right.
that can be
Right.
lifted.
Right. Yes. That's right. So yes, both of you are right. So if you can draw this without lifting pin, then also you will get the answer, right? But it is not the only way to do that, right? Yes, it's not the only way. If you can draw this graph without lifting pen, then of course you will get one schedule satisfying this property. But that's not the only way to do it. As someone pointed out, who told this? Yes, that's very important. You can actually even if you can draw this without lifting pen, then also you can have some schedule. Now the question is, what is the schedule? Can you list me? Can you give me the schedule for this problem?
Yes, ma'am.
Yes.
It's 1, 2, 3,
Okay. 1, 2, 3. Then
3, 4, 5,
okay. 3, 4, 5. Yes.
5, 6, 1,
5, 6, 1.
1,
Then
7, 4, 1, 7, 4,
1, 7, 4. Okay.
5, 7, 2,
5, 7, 2. Okay.
2, 6, 4,
2, 6, 4.
6, 7, 3.
6, 7, 3. Okay. Yes. Good. And is it the only option to do this in this way? You can get multiple way, right? For example, you can actually write any cyclic order of this also will give you the same, will satisfy the
Yes.
same thing, right? Okay. Good. Very good. So who gave this answer? Himanshu?
I'm Anshuman.
Anshuman Panda. Okay, thank you, Anshuman. Yes, that's the correct answer. Good, very good. So you have understood, right? So this is basically I mean, not only this puzzle, one can ask several puzzles and whose answer is basically this phenoplane. Okay, so that's why, or maybe some finite projective plane. So that's why that was the main motivation people had started asking question like this. But later on, people found that it is connected with something other more important thing also. Okay. Okay, I think today we don't have much time, so I can stop today and I can ask you some simple question, right? So for example, try to come up with one finite projective plane with some prime number, prime. Okay, so you don't know what is that, right? Okay, maybe. Okay, let me ask you some other questions. For example, are you familiar with finite field and all these type of things? Are you familiar with? You have. I hope mathematics students already know finite fields and all. So how about others? So is it the thing you already know it, or do we need to brush it up? What do you think? So because sometimes I think we need the idea or some basic idea, not even, I mean, maybe
It was not covered in discrete maths. It was
it
not
was not
taught.
but it was not covered, but that is okay. But I mean, did you learn finite field in some course, for example, abstract algebra or something? Was it a part of your curriculum? Was it a part of your curriculum at any point of time? Anshuman?
Not in any core course.
Not any course, but you know, right? Otherwise, I mean, it would. Yes, some other voice I got.
It's taught
Please.
in algebra, but I'm not sure if everyone from the math department has taken that course.
Even for mathematics, I mean, for mathematics department also, you don't know finite field and all. You don't know how to construct finite field, you know. So I'll give some prime or maybe some prime power k. Then of that order, how to construct one prime, I mean one field, right? Such kind of thing have you learned? So maybe okay. If you don't know, then I'll see how much background do you need. Based on that, maybe some what should I do? I'll again then some basic one lecture or half lecture I will spend. Next day lecture maybe I'll cover. Oh, and okay. How about so then I do you guys don't know modular arithmetic? This thing is known, modular arithmetic.
We did see that in discrete math.
Okay, no, okay, in discrete math you didn't see, okay, I see.
We did see that in discrete math.
Okay, you saw it, right? Okay, then I think, yeah, so I think then that would be easier. So maybe you can brush up the idea of modular arithmetic, so that, I mean, we can go forward, right? We need to learn something more using those modular arithmetic, okay? Knowing modular arithmetic also would be, I think, suffice. You don't need, as I said, finite fields means I don't need very deep knowledge in finite field, but some basic properties are required. So that if you know modular arithmetic, then that would be suffice. I hope so. Okay. If not, I will just point out which are the properties we are going to use. Using that, you can do. Okay. Okay. I think with that, do you have any questions? We are running out of time. Do you have any question? Any question? Okay, if not, let's conclude today's class. Next day, we will again see finite projective planes in detail. In the meantime, you can try with small numbers. For example, let's say if the cardinality of x is something, let's say 4, 5, 3. So can you draw one finite projective plane? So you can try, have a try, just to habituate with this constructing finite positive plane is not so much easy. Just to have that flavor, you may try with constructing finite positive planes having 3 elements in it, 3 points or 4 points, 5 points. You can try. Okay, with that, maybe I will conclude if you don't have any questions. If you have any question, please feel free to ask me.
Ma'am, what are the references we can use?
Right. That's a good question. Okay, good. So good that you, okay. So for regular polyhedron, right? So that part you will actually find in any standard textbook. For example, this book also will be suffice. Invitation to Discrete Mathematics. I think this Discrete Mathematics by Matusek. Matusek. I should check the author's surname. Name, right? Matusek. And this book, I think I have gave the reference in the first day itself. So from this book, you will be able to get the regular polyhedron part. Okay, regular polyhedron you will get from here, and the finite projective planes, that actually basically the book which I mentioned last class means the Brualdi book, introductory commentaries or something like that. I forgot the exact name, but the book which we mentioned in the last class, the same book, in the same book you will find finite projective planes and all. Okay. And the regular polyhedron part, you will find this in Invitation to Discrete Mathematics, and that too you search for this graph, planar graph. So this will be under planar graph. Chapter maybe I can tell you. That would be good if you can see. Planar graph, right? I think there is drawing graphs in the plane, right? So chapter 6. Right. Planar graph, chapter 6, in that you will find that the proof regarding regular polyhedron, which I just said. And the finite projective plane, right. So, yes, I think, yes. Both the thing you will be able to find it in Invitation to Discrete Mathematics. Okay. Both the things, finite projective planes as well as the regular polyhedron, both the things you will be able to find in this Invitation to Discrete Mathematics book. As a reference, you can see the other books also. Other book means that Brualdi book, that also you can see. But in that Brualdi book, you may not find this regular polyhedron part. Okay, do you have any other questions? Any other question apart from these references? Any other question? No question? No questions? Okay, then maybe we can conclude today's lecture. Right, we will continue this finite projective planes in the next class. Okay. Okay. Thank you, everybody. Take care. Stay safe. Okay, bye.